Okay, hello, this is the shelves and washer method video. I'm going to try to do this in one take. We'll see how that goes, eh? So, what first you need to know is kind of what we're doing. So in Calc 2, or whichever calculus you're doing right now that involves this, we're finding areas under curves. Okay, so this is like point A, this was point B. Alright, just trying to find this area. And this was the function f of x. Now, to find this area, we could use the integral from a to b of f of x, correct? And we could integrate it, and we get the area. And that's equal to the area. So now, another rendition of that is actually, what if there was another function, like right here, called g of x, and instead we want to find the area between these two curves? Well, we could think about it two ways, okay? You could either find this total area of f of x, which we found here, and then subtract off the area under g of x. So that would look like integral of a to b of f of x dx. So that's the whole area under f of x. Subtract the integral of g of x over that same interval. So the integral of this was just this smaller bit under g of x. And by subtracting this smaller bit, you'll get this area in between the two functions. But you can also think about it a different way. So when you integrate, you're actually using rectangles. I don't know if you remember that. So when you integrate, you're using rectangles. And what the integral sign means is, or like this function inside the integral, it's saying at whatever value of x, this is the height of it, of the rectangle, times the width of the rectangle, which gives you the area of one rectangle. That may be a convoluted, what I just said there. Like, I don't know if you can understand that, but here goes nothing. So another way to think about this, the area between two curves, is using these rectangles. So draw the rectangle if you were to do it this way. So this is f of x, this is g of x, b, and this is a. Okay, now think about this. So here in this initial one, if you think back to before I drew this g of x function, we are using rectangles, the height of f of x, and adding them up horizontally to get the total area. Now, we're using height of rectangles to find the area in between these two functions. The height of f of x minus g of x. That's the height of this rectangle at any given second. Here, under g of x, so if we were just finding the area underneath g of x, right here, the height of this rectangle was just g of x. But here, in between the two curves, okay, the height of one rectangle is f of x minus g of x on the same interval, because that's where the rectangles are being added up on from a to b. And if you notice, these two do the exact same thing. So in this case, we found the area between the two functions by finding the overall area of f of x, the bigger area, subtracting the smaller area. But in this one, we just found the different height, or the height of the rectangle, which is f of x minus g of x, and then we added it up. Okay, now this is important. The reason why I talked about this is because I just had to give you an understanding of what we're talking about. So now, what we're doing is we're taking this area, okay, we'll draw it back, b f of x, g of x, okay, now we're taking this area, and what we're doing is we're actually rotating it around the x-axis or the y-axis, and we're making three-dimensional shapes in doing so. So if we rotate this area around the x-axis, we'll get this weird, like, this weird sorry, I just got a notification. So we're not finding the area of the 3D shapes, we're finding the volume, because if you take this area and you just rotate it around and you find the area every given different rotation, you'll end up getting the volume. So to find the volume of this, we can think about it like this. So this is rotating around the x-axis and it gives you this shape. Okay, think about it this way. Let's take one rectangle. And this rectangle had height. This rectangle, so we'll draw over here. This rectangle has height f of x minus g of x. So that's the height of that rectangle. And let's look at this where this rectangle goes when we rotate it around the x-axis. Look at the outline that it makes. It's very difficult to draw. I don't know why, but I said I'll do it in one take, and I need to fix this somehow. I'm going to scratch it out. My apologies. So, although it's not drawn to proportions, this height right here is actually one rectangle. It's being rotated around excuse me, sorry, around this x-axis, which is right here. Okay, and that's the outline it makes. So by looking at one rectangle, and we can find the volume of this one rectangle, and then in doing so, we can use the integral to find the volume of all the other rectangles. In other words, we find the function. We can find a function defined by x such that we can add up different rectangles at different places. Oh God. You'll see. So this one rectangle is defined by two functions of x. And we could define the volume of this washer, hence this is what washer method is, of this washer, and we can define it by functions of x as well. So let's find the volume of this, because by finding the volume of this, we can find the volume of this overall creature. It looks like a sea, what are they called? I can't remember. Sea sponge? I don't know. Okay, so how do we find this volume? Well, notice, what's the area, or what's the volume of a cylinder first off? So the volume of a cylinder is pi r squared multiplied by h. So what this means is pi r squared is the face of the circle, and it's just being multiplied by h, the height. So we can use this to our advantage. And this, if you flip it on, if you go like this is just a cylinder. Okay? Did I say circle for this? I can't remember. This is just a cylinder. Now this cylinder has height dx because we're changing in the x direction here. and its face area, well, the area of the face, I'm just calling it AF, area of face, is equal to the bigger area, which is pi r2 squared, we'll call it, minus pi r1 squared. Okay, now what is this r2? Well, also I'll take out this pi, okay? Well, this r2 means radius 2, and I'm going to use that description as the furthest radius. Now this radius is the point from the x-axis out to the farthest. And, well, what is that? Well, look on our picture here. From x-axis out to the furthest point, well, that's f of x. So radius 2 is f of x. And we're going to square it. Is that how you denote squared for functions? I don't know. And then we'll subtract r1 squared, which is the smaller radius out to this inner ring, which is, well, if you look at the diagram, that's g of x. Square that as well, because it's squared. Now to find the volume, you just multiply it by the height, which was dx. So and square that. Okay, perfect. Now, using this, so this is the volume of this one washer. So this is washer method. And we can find the volume of all the washers, or the overall volume of this thing, by using an integral. So we can integrate this volume of 1. So pi, sorry, you're not going to see for a sec. F of x squared minus g of x squared multiplied by dx from A to B is the volume total, Vt. Perfect. So this is the washer method. And you knew it was the washer method because the shape that one of these rectangles made. That's the key part in understanding what the washer method is. Okay. So, what's the shells method? Well, I'll show you. I just have to think on my head right now because I'm doing this one take. What's a good example? Shells method. Okay, I got it. So instead, we'll take kind of the same shape. So act if I didn't tell you this was the shells method, okay? It'll help you. So this function is f of x, and this function is g of x, correct? And this height is a, this height is b. We're going to find the volume when it rotates around the x-axis of this bounded area. So notice in this case, the rectangles that we can use to do this integral can only go horizontal. And why is that? Well, take a second to look at this. If we were to use vertical rectangles at this point, let's say we're trying to make a vertical rectangle here, theirs is kind of weird looking because this vertical rectangle gets interrupted by the function of f of x. So if you were to do vertical rectangles, you would have to break it up at you'd have to break it up at different function points, and you'd honestly have to do like 3 integrals right there. But if you can do one, you can do one integral if you do horizontal, because it's, I don't know how to describe it. This doesn't work because Like it would work from, you could do vertical rectangle from here to here, okay? But then you can't get into these little nooks and crannies using vertical unless you do multiple different integrals. So that is why, that's another video. I think you should be able to know why. This is the vertical, horizontal rectangles we're doing, revolving around the x-axis. So look at one rectangle. Look at the shape it makes when it rotates around the axis. Okay? So it kind of looks like this, but it's really elongated. It has a big width to it. And this width, funny enough, is actually the height, the length of this rectangle. Length of this rectangle is, well, g of x minus f of x. Does that make sense? Because this is how big the rectangle is. The bigger height, which is g of x, minus the smaller height, which is f of x, equals the middle length. And, well, this little bit right here is actually dy, the tiny change in the y direction. Okay? So, I actually drew this wrong. These should be functions of y. And these should be functions of y because this is weird because, like, this should be functions of y because you're integrating with respect to dy. And on like a test, these might be functions of x, okay? But you want to change them into functions of y. So you can integrate with respect to dy. Maybe the question won't let you, so then you're going to have to do vertical rectangles and integrate with respect to dx. That's a lot to take in. I don't know if you understand it, but it's okay. It's okay. How do I focus? Okay. So now, goal is find the volume of one of these guys. Also, the overall shape of this guy is like very, like if we were to add up all these, it's very weird looking. I definitely won't be able to draw it. It's just like, it's lots of layers. It's called the shells. Like it's like, you know, like, I'm not gonna draw it actually. You know those Russian nesting dolls? It's like you put one inside the other, one inside the other. Like it's like this is a smaller shell, and then a shell goes over top, and another shell goes over top. It's kind of like that. Hence, this is the shells method. So again, I'm going to repeat it. It's defined by the way it looks. This is how I like to do it. So you know you're doing the shells method because, well, this is the picture that it makes when you rotate it around the axis. So you don't really have to memorize some weird intricacies to remember it. Just look at it, what the shape it makes when you rotate it around the axis, okay? So, how's the volume of this? Well, let's chop it right here. Let's chop it right here. Let's take scissors and snip it, okay? And by snipping it, you can unravel it. You can unravel this and get, well, you can get a rectangle now, width dy, I guess like depth dy. I don't know how to really define it. This, we'll call this other width, okay? Well, that stays the same, gy minus fy. Now, what's his height? Well, his height is the overall circumference of the circle. And the circumference of a circle, well, circumference of a circle is equal to 2 pi r. But in this case, r, our radius from the middle, so this is the x-axis, our radius from the middle, which is the x-axis, to the outside. Look on the picture. Axis to the outside, or to the bar that we're rotating around. This is whatever the y value was at that time. So that's why we give y. It's a variable. This circumference changes with the change of the circumference changes of the shell depending upon what level of y you're on. So that's why it's a function of y. It's 2 pi y, correct? And now you know the volume of 1. You can find the volume of all these shells at every given dang spot. So like right there, right there. I don't know if that really helps the analogy. I just like scribbling. So we're going from A, bottom, to the top, which is B. And the volume of this is just 2 pi y multiplied by g of y minus f of y times dy. This gives you the volume of one boy here, and by integrating over this interval you can get all the volumes of the shells. Does that make sense? I hope so. Filmed in one take. I know it wasn't the best, but I think it could, by watching this, you can get more in-depth analysis into like how to remember and how it all works. Kind of just like talking out of my butt a little bit, but thank you for